Welcome to Dr. CM Edcast, your go-to resource for medical learning. Through discussions, case studies, tutorials, and debates, we help you learn, grow, serve.
All right, our journey begins at the very start with the formation of the primordial heart tube. This is the foundation, the scaffold upon which everything else is going to be constructed. So where does the heart even come from? Well, its origin is in a specific germ layer called the splanchnic mesoderm. Around day 18, in a region known as the cardiogenic area, the very first cells that are destined to become the heart just appear. And what's really fascinating is its location. At this early stage, it's actually cranial, or above the developing mouth. Kind of weird, right? But that's all going to change dramatically with embryonic folding, as we'll see in a moment. Now, here's something that might surprise you. The heart doesn't start as one structure. It actually begins as two completely separate tubes, the endocardial heart tubes, which you can see here on either side of the embryo's midline. These things arise from little cords of cells called angioplastic cords. The next crucial step is a major morphogenetic process, folding. Think of the flat embryonic disc starting to fold laterally, kind of like closing a book. This movement is what brings those two separate heart tubes towards the center. And here's the result of that folding. The two tubes meet right in the midline, and they fuse together, forming one single primitive endocardial heart tube. This fusion is an absolutely critical event. It establishes the single channel that's going to become the basis for the entire heart. Now, around day 22 to 23, something truly remarkable happens. This brand new, simple tube begins to beat. Just think about that for a second. This marks the beginning of the cardiovascular system, the very first functional organ system to develop in the embryo. But, a simple tube isn't going to cut it. It now needs to get that complex, three-dimensional shape of a real heart. So how does it do that? Well, through a process called cardiac looping. The reason for this looping is basically a physics problem, a real estate problem, really. The heart tube is growing and elongating really fast, but the little sac it's sitting in, the pericardial sac, isn't growing nearly as quickly. So the only way for it to fit is to bend and fold back on itself. We can see that dynamic process in action right here, happening between day 23 and day 35. The tube bends, usually to the right, and it creates a C-shaped loop. The part that's going to become the ventricle moves down and forward, while the future atrial region moves up and backwards. So, what's the big takeaway from all this looping? By the end of it, we have a basic blueprint. The primordial atrium is now positioned dorsally, or behind, the primordial ventricle. And that establishes the fundamental spatial relationship we see in the adult heart. This is a huge step forward in building that four-chambered heart. Okay, so we've got the basic layout, but it's still just one continuous channel. Now we get to the climax of our story, partitioning or septation. This is the incredibly intricate process of building the walls that will divide this single tube into a four-chambered heart. And get this all happens incredibly fast. The entire process of dividing the atria, the ventricles, and the great vessels, it all kicks off in the middle of week 4 and is pretty much complete by the end of week 5. It's just an astonishing pace. This complex job happens in 4 coordinated stages. It's like a checklist. First, you have to divide the channel between the atrium and ventricle. Then, you separate the atria. Next up, the ventricles. And finally, that single outflow tract has to be split into the aorta and the pulmonary trunk. Let's start with the atria. The first step is the growth of a thin, crescent-shaped wall. It's called the septum primum. It grows down from the roof of the common atrium, heading towards these structures called the endocardial cushions, which are forming right in the center of the heart. Now, this is just a beautiful and elegant mechanism. The septum primum doesn't close the gap completely at first. As it's growing down, another, more muscular wall, the septum secundum, grows just to its right. Look at how their staggered growth and overlapping layout create a one-way flat valve. This is the foramen ovale, and it's absolutely essential for shunting blood in the fetal circulation. A failure in this intricate little dance can lead to an atrial septal defect if that foramen doesn't close properly after birth. This really underscores why this whole process is so clinically relevant. The complexity and precision required mean that even small errors in septation can lead to significant problems, and that makes these events a primary cause of congenital heart disease. Okay, with the chambers now partitioned, let's look at how these early embryonic structures get remodeled into their final adult forms. We'll start with this sinus venosus, which was the heart's initial collecting chamber. So, back in the embryo, the sinus venosus basically acts as the inflow tract, the inbox for all the returning blood. It has two horns, a right and a left, and each one receives venous blood from three very different places: the common cardinal vein from the body, the vitelline vein from the yolk sac, and the umbilical vein coming from the placenta. As development moves along, the whole circulatory system shifts, and that right horn becomes the dominant one. And this right here is a perfect illustration of the direct link between embryology and adult anatomy. That right horn gets absorbed directly into the developing right atrium, and it forms its smooth posterior wall, which we call the sinus venarum. And this explains why the atria actually have two distinctly different textures. In both atria, the rough, muscular, trabeculated part, that's the original primordial atrium. But the smooth part, that has a different origin. In the right atrium, it comes from that absorbed right horn of the sinus venosus. And in the left atrium, it's formed by the absorption of the primordial pulmonary veins. All right, let's wrap this up by connecting these developmental events to specific clinical conditions, because understanding how the heart is built is really the key to understanding how it can go wrong. This table is a great high-yield summary. So look, if atrial septation completely fails during weeks 4 and 5, you get a common atrium. If that final piece of the interventricular septum fails to form in week 5, you can get a ventricular septal defect, or VSD. And if the partitioning of that big outflow tract is unequal, you get that classic constellation of defects known as tetralogy of Fallot. The key thing to remember is that each of these anomalies is a direct result of a failure at a very specific time and place during development. So we've seen how the complex anatomy of the heart is a direct reflection of its embryonic journey, which kind of leaves us with a final thought. What other parts of our bodies carry these echoes of their development? And what stories could they tell us if we only knew how to look?